All right, well, I guess you'll be the audience for this. This is the camera that I got whenever I got it. And while the truth of the matter is that these are not used that often, for historical purposes, I think it's kind of interesting to see one of these things run and to hear it. So the door can be taken off. You can see the threading path is rather simple. And I'll do that. I'm putting in 100 feet of film, and that's enough for 4,000 pictures. There's 40 frames a foot. And so there's the drum with the sprockets on it. That's going to pull on the film. And also the motor, there's a motor on the bottom shaft. So this one pulls, this one also pulls. But actually, this is the one that pays out the film. This kind of keeps it tensed. And there is a mechanism for actually forcing the film onto the teeth, because at high speeds it doesn't want to do that, and if it doesn't get onto the teeth, then it jams. So there's a hold down roller, and there's also a switch in it that senses whether there's film in the camera or not. If there isn't, it comes out, power is cut off, and the camera stops. So we'll take this. Now if you load 4,000 pictures into the possibility or storage for 4,000 pictures, and you run the camera at 4,000 pictures a second, you can imagine how long you're going to have film for. Now that's the same thing with digital. Storage is limited, and you have to think about, well, this is how much I can do, and if I spend it at this rate, how much time am I going to have left to actually make the pictures? So in this case, we put 4,000 places where you can put images, and while normally the camera, you know, you'd have all the other things that would go along with a high-speed experiment. You have a subject there. You have to consider lighting. Do I have enough to expose each of the frames at the proper level? But we'll ignore all of that, and because this is a historical thing. It's just so that you could see what people used to do. With these, it's kind of useful to remember to make sure that all the switches are on the off position before you plug it in. So we have essentially power that could go here. And then when you're ready to run the experiment, normally you wouldn't run it with the door open, okay? But you're far enough away from me, I think it's okay. And when you want the camera to make the photographs, you just flick a switch. You just made 4,000 pictures. Okay, so now that'll take you about 2.5 to 3 minutes to watch it projected. So it's an experience. Okay? Not that, but at least you can say, oh, I saw one of these run. Now, you all want to see this too?
Yeah. I saw it in your demo last year, but I'd love to see it again.
Who's out there?
Oh, Ross.
Oh.
Ross!
Oh, sorry.
All right. So we'll run it again for the latecomers here. Oh, first thing to first, make sure the power's on. Because if the power's on and you touch that switch, the camera says, oh, there's film in it, and I'll run.
Oh dear.
Yeah, you don't want to do that. It doesn't really hurt you too bad, just puts a scratch in your finger.
David. Now, is anyone taking high-speed footage of a high-speed camera running?
I think that's been done, but you can do it. So often I'm asked, well, won't you expose the film? Yeah, about 3 or 4 feet of it. So it's okay.
How much did a roll of film like that cost?
Yeah, that's the problem. That's one of the reasons that I stopped using. For students, it was just too expensive. Between the cost of the film and processing, you're talking about $60 for maybe $70 for 100 feet.
Yeah.
And then, of course, as they say in photography, if it doesn't come out, it's $70 down the tubes.
Right.
And there are many reasons that it might not work. But this camera is worked like a charm. So anyway, load it up again, and when you're ready to go, we go, and here goes. So this is what it used to be. Now they don't make any noise anymore.
Wait a minute. Wait.
Yeah.
Okay.
That's 100 feet.
Wait, it sounds.
Crazy.
Wait, that was 100 feet?
That's 100 feet. It's 4,000 frames.
Trying to think of the last 100 feet. 4,000 frames.
Okay, now I gotta figure out what else I was gonna do. Well, I guess I'm not that enamored with digital systems partially because it's hard to relate to them. They're electronic. You don't see photons. You don't see gears, cams. They don't make any noise. They just heat up sometimes. And they burn. It's not good. But there are very strong analogies between film systems and digital systems. In high-speed photography, whether either one of them, the things that you want in a photograph is you want your photographs to be good and sharp. You want resolution. One way to accomplish that is to have large images. Thinking about the film world, 4x5, bigger image than the 35, bigger image than the 16. So the larger the film format, you can expect better resolution in the final product. The other way in the film realm is to use finer grain film. Well, in the digital realm, that also is the case. You can have big pixels or you can have small pixels. It turns out that essentially, at some point or another, it's a trade-off between how big you want the sensor to be versus what kind of lenses you have to put an image on the sensor. And the bigger the sensors, the more expensive they are, the more difficult they are to make. So typically they started out small. Now they're starting to get a little bit bigger. But sensor size or film size controls something about resolution. So you want this. What else do you want? You want speed. You want, the higher the framing rate that you can achieve, the better. Whether you use it or not. So from a builder's point of view, they don't care. If they can say that my camera does 1 million pictures per second and yours does only 500,000, okay, so it's better. The kind of framing rate is going to be dependent on your needs. But at some point or another, you're going to say, I want high speed, because low speed is not high speed photography. Right? But capturing images or recording them at a high rate is problematic. you have a bit of information that's that big, okay, and you're gonna transmit it somewhere, the computer, or whatever, the data in this image file, in order for it to go through there, to there, it has to go through this, whatever that is. Well, this is essentially a bottleneck. It says, I can only pass so much information through me in a given amount of time. So if that bit of information is equal to what's in here, then you have reached the limit of your transmission capability, or recording, or whatever it is. So how can you increase the framing rate when this is your limitation? Well, what you can do is you take this and you break it in two. So now you send this one, and then you send that one, but at the same rate. So in this amount of time, now you're sending two pictures, so your rate has doubled. But your picture size has dropped. So it's a trade-off. You want higher speed? Smaller images. Now you can go further, you can go that way, or then you can go this way. And you make the frame smaller, the bits of information smaller and smaller, and you still transmit at the top speed that you can, your framing rates are going to go up. The same in the film world. In the film world, we had 16mm frames like this. The cameras would go 10,000 pictures a second. Well, you cut the frame in half, and you can go 20,000 pictures a second. Your resolution has dropped. Total bit of information. Or you can go to an eighth frame, quarter frame. In the digital world, exactly the same thing. You have so much space, so much capability of moving it, and you can move smaller images faster, but not the big ones. They will limit the top rate of the camera. So you might say, well, I'm not sure what you would say. We're going to say, you might say, what is it? Well, what you eventually arrive at is a compromise. It's a trade-off. I want the speed, I will live with lower resolution. That's the way it goes. And the manufacturers will essentially do the same thing for you. They will provide cameras that do 1 million pictures per second, but if you look at the file size of those, or the image size, they may be 64 by 64 pixels. Is that good enough? If you're trying to detect whether a switch is closed or open, probably is. If you're trying to figure out whether an athlete is doing something properly, probably not. And the other important factor that you deal with, again, this is a photographic requirement, that the amount of light that is falling on the subject be enough to produce some kind of a signal in the camera, whether digital or film. So that has to do with sensitivity. You want the sensor, or whatever, to have high sensitivity so that you can use low amounts of light. Now, there are many reasons why you want to use low amounts of light, not necessarily because of the camera system, but because of your subject. You're photographing a fly flying around, and then you concentrate the power of the sun through a loop on the fly, and it burns out. Any of you burned up ants with a magnifying glass? Well, you know how that works. So, you may have the ability to have lots of light, but that's going to impact on your subject. The subject is going to dictate, I can't tolerate a lot of light. And in that case, what do you do? Well, you have to have sensitivity. How do you get sensitivity in the digital realm? And actually the film realm too. Well, you have little teeny pixels like this, or you can have big ones. Well, the big ones collect more light, right? Yeah, but all of a sudden, now your sensor gets bigger for the same number of pixels. And you can't cover it with the lenses that you have. So these factors are competing against each other. all the time, as the camera systems are being manufactured or designed. And then it's customer choice, yours, as to, well, what is it that you need? There are ways, but ultimately, I was going to say, there are ways to increase the sensitivity of a camera. Typically, it comes at the cost of some loss in resolution. Well, so I just said, you're compromising again. It always happens. But there are methods by which speed can be tremendously increased, typically in high-speed systems. They're using something called a micro-channel plate, and that's just a bunch of little tubes, and all stacked on top of each other, and you put an image on one side, you put electricity around it, and out comes more photons on the other side than they're going in. So you amplify them. We're not going to get into them, but it is an alternative in high-speed photography to amplify the light level somehow. Now, one thing that personally I'm kind of interested in is the concept of realizing that that you need a certain amount of light to make a properly exposed, properly recorded kind of image. I'm going off on a direction that I haven't really gone in before, so I'm kind of making it up. I just happen to remember. How many of you are familiar with the Sunny 16 rule? Most of you. Do you know why the Sunny 16 rule works? You know that, yeah, on a bright sunny day, I expose at f16 at 1 over the ISO, right? And I should get an image which is pretty cool. So why does that work?
Coincidence?
What?
Coincidence?
Coincidence, yeah, right. I don't think so.
It's got to do with the way the ISO is calculated from. I mean, you get the ISO from calculating various things.
It could be some other thing, but no, it works. It works because there's a standard involved. There's a constant involved. And what's that constant? It's the statement that I just said, on a bright sunny day. The Sunny 16 rule doesn't work when it's cloudy. It works when it's sunny, when it's kind of a standard sunny day. And that means that there must be a certain light level present, provided by the sun. And it says, okay, under those conditions, those parameters are going to produce a properly exposed image. And that happens to be, well, how do you measure the amount of light that falls on a scene?
Light meter.
A light meter, right? You know, one of these. And you can, you know, that, and I think I mentioned this before, you can operate them in either mode, you know, reflected mode or incident mode. Typically, if you measure light that is falling on something, you use it in which mode? Incident mode, right? So you put the little dome over the sensor and put it there. So it's measuring how much light falls on it. And that is what the Sunny 16 rule works on. It says, on a bright sunny day, northern latitudes or mid-latitudes, the amount of light that falls on the scene is this much. And when that much falls on an 18% gray card, it will reproduce like an 18% or whatever reproduction in your recorded image. They're called light meters because they actually measure light. What they measure is something they measure foot candles, whatever they are. It's a description of how much light falls on a scene. And on a bright sunny day, there's 6,400 of them. Okay, so how does this work to help us determine whether we have enough light falling on a scene to properly expose the sensor or the film that we're going to use? Well, the relationship is this one. I think. Let's say foot candles is equal to this number, oops, 25, is a fudge factor. It's determined empirically. Times something divided by something. ISO is down here, times exposure time is down here, and this is F number squared. I believe that's the case. We can test this, because we know that on a bright sunny day it's 6,400. So I'm going to plug in 6,400. And I put a 25 here, and then I say 16 times 16. Oh man, I don't know what to do with that is. What is anybody else? 16 times 16, it's 166. Gotta be easy to figure that one out, isn't it?
256.
Oh,
256,
yeah, 256 is a familiar number, isn't it?
Yes.
It's one of those things that you gotta think about. So 256. Okay, and then we take the ISO, and let's say that we use a 100-speed film, a 100-speed sensor. Okay, so it'll be 100. And what does the Sunny 16 rule say? Well, use the reciprocal of the ISO, right? So our exposure time will be 100th of a second. So here's our F number, which is 16 that we squared. Down here is the exposure time. Here's the ISO that we're using. Well, this cancels out, doesn't it? 100 times 100th, 1. Isn't that right? Okay, so now we're left with 25 times 256. And Laura's doing it.
6,400.
How much?
6,400.
Wow,
Yeah, it works.
6,400. Okay, so this is pretty cool. Because now what we can do is, actually if we wanted to, we could recalibrate our meters, which are calibrated in F numbers and shutter speeds and so on, to read in foot candles. Actually, you don't have to do that. Because in the back of these, anyway, there's a chart that tells you when a particular meter reading is read, it's so many foot candles or meter candles. But you say, okay, well, I only have half of that. 3,200 foot candles. You measure it somehow. And what's the consequence of that? Well, it means you have to change this or this. Larger lens opening or longer exposure time to end up with a properly exposed scene. Now, how do you generate foot candles falling on a scene? You have a lamp. The lamp puts out a certain amount of light, and lamps. And put a lamp in a reflector over here. And typically, if you measure the brightness of the lamp or the intensity or whatever that falls on a scene, the scene is over here. Okay, you'll find that I'm drawing it upside down, so I'll put it over here. It goes like this. Okay, the center of the reflector sends more light than the edges, right? And so manufacturers tell you, how much goes forward and how much goes sideways, and so on. So this is like peak illumination or a certain angle. So, at 1 foot, it's so many foot candles, at 2 feet, it's so many foot candles, depends on what the distance is. So when you say, okay, I take this scene, whatever the scene happens to be, and I find that from here to here, I only get 3,200 foot candles from this one lamp. So what do? Well, I get another lamp. I figure out how many lamp fixtures I need in order to increase this to 6,400. If each one of them only illuminates to 640, I need 10 of them. And so you can estimate the number of lamps that you're going to need based on the manufacturer's supply data as to how much light the lamps put out. I'm saying it's like falling off a log, but it all kind of makes sense. It would be nice if you had just one lamp, and you could just regulate it. Sometimes that's not possible. So, what else was interesting? From a technical point of view, this little thing here is a neat relationship to keep in mind. It has many applications. Sunny 16. I will admit though that sometimes that number is changed to, that's sort of a constant. As I said, it's a fudge pattern. Some workers like to see that at 20 instead of 25. Usually it's lower than 25. Regardless. So let's see. We got to think about. Wow, I finished that a little faster than I wanted to. We can spend a little time thinking about tomorrow. Okay, tomorrow, it's sort of like the high-speed flash event. You bring a subject, and we photograph. But not everybody photographs the same thing this time. So you can have your own setup. And kind of the operational details of how the cameras are going to work are will be provided with the cameras that we have. One of the warnings that I had for you early on was the fact that we don't have many pieces of equipment, and this is one of the cases where we don't. We have one camera that is a pretty high-end camera. It's made by a company called Vision Research. And if you go to Vision Research on the web, they'll have lots of examples of what their cameras can do. However, what's been happening lately is that the cost of at least getting into high-speed motion photography has dropped considerably. And one company in particular, Casio, embarked in this process of making their cameras, some of their cameras, high-speed capable. And you can check one of these cameras out. They have one in the cage. I have one here. And I'm not sure how much they go for anymore, but when I got it, it was $1,000. I only buy cameras when they're less than $1,000 or there. So when this came to $1,000, yeah, I think I can afford that. It looks like any old DSLR, right? Well, in movie mode, most of these cameras can run 30 pictures per second. So you put them in motion picture and 30 pictures per second. Well, what they did is I think they dropped the resolution some, but the camera, just as it sits, can do 300 pictures a second. They're full frame. So then, can you go faster? Well, yeah, Casio said, we'll do what I just told you before. We'll cut the frame in half. So your pictures are now a little bit not as tall. They're half as tall, same as wide. But the camera then runs 600 pictures per second. And they went one step further. They said, oh, well, we'll cut the half in half. So now they're quarter size. Your pictures are more like this. Yeah, but the camera now runs 1,200 pictures per second. And 1,000 pictures per second is something. Yeah, your frames are kind of weird. I think the newer models, and what Casio did in this case, and all the high-speed camera people do, they said, well, we'll split the frame in half. It's kind of logical. And then we'll split the frame in half again. But you have a weird aspect ratio, right? But in the digital world, you don't have to do this. What you could do is something else. You could do this. Right? Or you could do this. Now you preserve the more rectangular aspect ratio instead of that long one. Sure, your resolution drops. But that's the trade-off, remember. Trade-off, speed, or resolution. And that's what they do. So I think the newer cameras let you do this. You know, the first ones didn't do that. But it's kind of neat. This is rather simple to operate. And I would bet that a large number of high-speed applications can be solved with a camera that does, I like to say 600 pictures per second, because half frame is really not bad. You know, it's a little bit longer and a little more kind of landscaping, but it's not obnoxious like this one. And I've done consulting jobs with that. So, well, I can do 600 pictures per second. Fine. And not only that, the camera, and all of these cameras do, you have the framing rate that you can adjust, but then the other important thing is to be able to adjust the exposure time. Because you could have a frame time that lasts that long, and if the exposure time is that long also, well, the subject is going to, or the image is going to blur. So what you'd like is the exposure time to be this long, okay, to capture sharp pictures of the moving subject, and then you have whatever framing rate is associated with that. This is visible. I'm not sure how many of you watch. I think it's mostly, I noticed it in tennis, high-speed recording of tennis, because you tend to see the ball as very sharp images instead of kind of blending into a blur when it flies. That's an indication that the camera was set to a short exposure time. You couldn't go any faster, but the exposure time was short. Visually, sometimes that's not a good thing because you can see the ball here or there. But technically, it's tour de force. So technically, this is what you want. Visually, you want the blurry one. So because one of these is available in the cage, you can borrow it. You can actually borrow mine too if you want. Just let me know. And then we'll have another camera, the Vision Research camera. I think it's right here. It's $20,000 right there. And that splits the frame just like this one does, except in more pieces if you want it to. It can do 1,000 pictures per second that are as big as the sensor gets. After that, you start to cut it down. And but it's a little more difficult to operate. It's got a computer hookup, and it stores the pictures on the camera, the images, and then you have to download it. However, the images that it makes are quite nice. So what I'd like to do, we just got a few minutes left, is to show you a few examples. Oh, I can't show you. We don't have enough time for all of them. So what I'll do is, maybe as we're working on tomorrow, I wonder if this will work now. I can show you some more. Any questions?
Anything you recommend bringing in?
Well, you'll see some samples of them. You could bring in somebody you don't like.
Yes.
No.
Yes.
No.
Then you said last year.
You said you could.
Last year we could.
All right, let's see if I can find it. I didn't know we were going to have this opportunity. When I said that.
Oh, you said you would when we had the opportunity for National Key High Speed. You didn't do it. Oh, that's kind of busy. Right. Which one?
Let's see.
Over here. Okay. I assume you
Okay,
can't
this was
bring it.
something I did for the Rochester Police Department. They wanted the pistols to show how the ejection mechanism worked. Make this bigger.
Yeah, you should be able to just drag.
Okay, so that's kind of, you can sort of see it. This was an early generation digital system, except it used tape. And we're running at 1,000 pictures a second. And I think it's running now. We did that right in this lab right here. You can see the thing going there, boom.
Yeah.
Here's the smaller frames. It's running still 1,000 pictures per second, but it's like 6,000 pictures a second because sixth frame, or is it 5 frames? So 5,000 pictures a second. And you saw that. I think we'll see it again with this gun. That the gun looks different from one frame to the next. You'd expect that. But so this, you could call it a forensic application or a law enforcement application, whatever, a mechanical application. So on the camera, I guess we're done with this one. And let's see.
We do punch slap flick one.
You want to do that one?
Yes.
Of course.
Most
Okay.
things we want to slap down.
Yes.
So,
Dave sounds on board.
Yep.
I like the haircut.
Yeah.
And the hair follows the head.
Yeah, I know.
It's like pushing it.
Please yours won't be that.
We're not doing that.
Okay.
That's fair.
That is fair. Oh. This is perfect about how it like moves back and forth.
I guess it hurt.
I love how long the reaction time is between the impact and the face being able to this. This is so cool.
Okay, here's the Casio photographing things being dropped into a martini glass. Uh, 1,200 pictures per second. In this case, so that's the frame, but it was turned on its side, so the camera was whatever. I mean, the quality of this is really not bad.
Very reasonable. Like you can see the light flickering in the background.
Oh yeah, no, I should mention that. If you have fluorescent, but actually even with tungsten lamps, the high-speed cameras, when they're not synced with the lights, they will probably make visible flicker of the lamps that did not synchronize properly. So in the high-speed industry, they are sometimes quite concerned with that, and they use lamps that are specially stabilized to have constant output. All right, now this, the next bit is going to be a bunch of events that were done many years ago, but that shouldn't, hopefully doesn't bother you. That were done on film. There's no sound, unfortunately.
Oh, thanks, dropping. Oh, that's cool.
So whatever you bring, I mean, it obviously can't be way too big. On the other hand, you don't have to do this tomorrow. You can do a high-speed sequence some other time. The only thing that I ask is that when you make this, you make some measurement based on the image. Oh, I have another thought. You will get a standard image from me, a standard movie, and you can make a measurement from that, or you can make a measurement from the photographs that you make. Like how long something lasts, that would be good enough. So it's not just a visual. That moving of the image up and down, that's typical of the rotating prism cameras. Because they have gears that have to mesh, and sometimes they don't mesh quite properly. It's a piece of golf ball going through a glass. Yeah, I think that's what. At the time, they also did a golf ball going through a telephone book. It was kind of hard. They did do it. This is kind of neat. Toothpaste.
Weird.
And I think this next one. No, not this one. The one after this. This is just a poor. Probably a rotating prism camera that was used to do this was not the right kind of camera to use. You could have used 500 pictures per second with a pin registered camera, and the image would have been much sharper and clearer. Oh, this is neat.
What?
Is that a ferret?
No, it's a rat. Well, he got to the surface quick.
You would too.
Well, yeah.
Dropped in the tank with a can of water.
Unfortunately, no animals.
No.
I don't want the SPCA to come knocking on my door again.
Again.
Well, yeah, they came once. I told you about that, didn't I?
Yeah.
Yeah.
Yeah, I think so.
Well, last year somebody photographed a goldfish in a balloon or something. I think that flames are okay, and sometimes they are. This one, I think, was kind of a dud.
That's interesting. It could be.
Another glass shot. Comes a pellet. Didn't do much, did it? And, oh, and this is sort of like the being punched.
Is that a foot?
It's a foot coming down here.
Oh.
Oh. Yeah. Some jumping.
That's disturbing.
We are flabby creatures, aren't we?
Yeah. Well, for a good reason.
Oh, God, no. I hope this isn't the same thing.
Water
No.
balloon?
Oh, nice.
It was gone before the
Yeah.
thing hit it.
I do like how it still hit. You can still see a dome of water when it impacted.
Yeah, yeah.
It was still that quick.
This is, the next one is another water balloon.
It was
Just
slow.
very small water.
Really large rat trap.
For you,
Oh,
Oh.
Is it jello?
Didn't do
Whoa.
anything. Yeah, it didn't break.
That's so weird. That is just strange.
That's even weirder, I think.
Yes, it is. Somehow that is just really, really weird.
Those are red jellies
So,
or Zelda that
Let's see if there's any,
The luckiest drop ever.
I could put my finger in the water.
Yeah.
no, I think we'll do with that one. So hopefully that gives you some idea, you know, nothing too big. And not everybody will be able to work with that camera, the other one is around. You will need to transfer data from the cameras to some kind of memory. So come prepared with something.
I'm actually okay with that.
Compact flash cards will work, I guess, on a computer. Yeah.
I'll do it again.
Working, I can-
Not at the same time.
Yeah.
No, Ben can slap me if I can slap that.
That's still not fair.
If you want to get a slap her, then you can slap me.
Last year, the,
Check it out.
You want to get a slap?
Slap Liz.
Imaginary, she brought her own, she has a, let's see, let's see.
It'd be like the,
All right, and if you're gonna check out the one on the page, let me know if they actually do have it.
Will do.
All right.
See you tomorrow.
No, no. Not anymore. Sure.
Yeah.
Yep.